Okay, a very good afternoon. So,
Good afternoon,
Good
sir.
afternoon, sir. Good
this,
afternoon, sir.
good afternoon. This is an initiation for CSR net classes. Expecting most of you could clear the CSR net in the coming session. So, I hope at least some of you have already appeared for the CSR net exam. So, so far you are already writing these academic exams. When you look for the competitive examination and the regular academic examination, there is a big difference between them. And apart from that, regarding CSIR NET exam, the one difficult task about this one is that the syllabus that it shares. It shares almost the entire chemistry syllabus. But the one important and one advantageous point of view is you will have more choice for writing the examination. There will be many questions that there are, I think, around you need to answer only around 50 to 60% of the questions. That means nearly half of the questions that you can make as a choice. You will be given a many number of questions. Among those, you need to ask, you need to answer a few. But since the syllabus is very large, whenever you are preparing for this examination, everyone must have a strategy to go for. Means how many number of topics. If you see, always have a look that please collect the previous year question papers. Okay, all the question papers are available. Even I have the question papers, so I can share with you all. Please look at that previous year question papers. I will be teaching you the thermodynamics and molecular spectroscopy. For thermodynamics and molecular spectroscopy, the chapter-wise questions I have collected and that I will share with you. Okay. So for qualifying this examination, what one should do is that you practice more number of questions. Okay. Try to develop the concept based upon practicing the questions. Even if you read the subject for 5 or 6 times, so without practice, if you go, it will make a confusion when you are writing an examination, because this exam is application of your knowledge to specific examples. So for the application of knowledge, one needs a lot of practice. You have to practice like as many questions as possible. You practice. The good point is we have all the questions available, previous year questions, and one more thing, that there will be repeated questions as well. Either sometimes, rarely you will get all complete the same question you will get in the next session, or many a times the same concept will be asked with different examples. So if you solve the previous year questions, all previous year questions, 20% of questions you can answer easily. And another thing is, some questions are memory based questions. Okay, so you just need to remember and tick the answer. That's it. Especially when you come to the inorganic chemistry, this bioinorganic chemistry topic, there will be definitely questions from that, and they are mostly the memory based questions. Okay, so one thing I observed when writing for CSR EGC, this net examination, is inorganic chemistry usually a scoring topic. So anyone, whether you choose physical or you choose organic, everyone means I suggest you that don't skip any inorganic. Okay, prepare for inorganic. That will be scoring you. That will make you qualify this net examination. And if already some of them are attended the examination and unfortunately could not make the barrier, so my suggestion for them is that increase the number of topics. Okay, don't read by chapter. Okay, even suppose thermodynamics, if you have thermodynamics is a huge syllabus, huge chapter. From that thermodynamics, there are sub topics available. Okay, so divide one big chapter into several subtopics possible, And from each subtopic, look at the questions that you are getting. So I will teach, when I am teaching this thermodynamics, I will teach you how to divide these topics. Okay, divide into small pieces of topics that will make your preparation easy and practice easy. So whenever you are not able to reach the barrier, you try to include the new topics into your preparation. One another important and one suggestion is that never skip spectroscopy. Okay, my usual observation is the older topics, like the topics that you started reading from +1, +2, and you are continuing till today until MSc. These are older topics. So one is expected to have a deep knowledge on these older topics like thermodynamics, chemical kinetics, these topics. There will be questions that very tricky and logical questions being asked because these are being taught to you from long time. So you are expected to have a very nice understanding on these topics. Whereas if you go to the master level topics, I mean, the topics that are introduced at final BSc, starting from final BS to BSc to master level, from there you will not get so tough questions. If you prepare those topics for you, they are kind of direct questions. If you practice some questions, you will get questions related to that only. Majorly, the examples are like NMR spectroscopy. So don't skip NMR spectroscopy. It is very, very important topic and scoring topic for CSIR net, and very useful for topic for researchers as well. Okay, any part of research you do, most of the chemistry researchers need to do NMR spectra and need to analyze the NMR spectra at some point of time. Okay, NMR is the one that I seriously suggest you to focus upon. Solve the as many questions as possible. There is a textbook called William King. Okay, we have some textbooks I will share with you. What you need to do is that read the topics first, and then try to solve as many questions as possible. Whatever the questions they have given, try to solve them. Okay, and if you solve 5 to 6 year papers of NMR spectroscopy, I'm 100% sure that you will score at least 5% in the CSIR net exam. Without preparation, you can score CSIR net 5 NMR questions easily once you have the practice. Okay, practice is the main key point in clearing this examination. I don't think it is a tough exam. Okay, so it's a big exam. It shares a lot of syllabus. That's why it makes difficult for students to clear. Okay, so whenever you have each time whenever I am teaching, I used to share my experiences with you, so that it can be helpful to you. Majorly here, I will discuss about thermodynamics and then molecular spectroscopy. If you see thermodynamics you are reading from +1 to intermediate level to even this PG level, where you study mostly the partial molar properties. And the molecular spectroscopy is a master level topic. So one older topic and new topic. So both are scoring topics. So I divided. I forgot to mention, but I am Dr. Srinivas Prapancharaj. Recently joined in the chemistry department. So when we are looking at the thermodynamics, I have divided this thermodynamics into few subtopics. Most of the topics you are already familiar with them. Starting from the basics, in the basics, I know that most of the basic terminologies, the parameters, the state functions, all you are familiar with that. But I would like to brush it up once before going for the equations for work equations. When you are doing work equations, you need to remember some basic points. And then we go for the first law of thermodynamics. In the first law of thermodynamics itself, we will discuss the internal energy, enthalpy, and then the Q values, Cp and Cv. From here, Next level of thermodynamics starts equation of states. Mostly there will be questions, there will be definite questions from the equation of state and Maxwell relations. So I will teach them with you with some tricks. Okay, so for some easy remembering tricks, there is a Maxwell square concept. You just write Maxwell square, and from that Maxwell square there are two tips. With the two tips you can directly answer the questions. So that this topic will be based upon the, of course, for exam point of view, I am teaching you with the tricks. Usually this is one of the very important topic to understand any thermodynamic process. Then this is thermodynamic coefficients, little deeper thermodynamics. And then Carnot cycle, you already know very well the Carnot cycle. Definitely, mostly you will be getting question on the Carnot cycle, Carnot engine efficiency, or there will be a graph between. Usually we know that PV graph is there. That is what we studied in +2 or BSc level. But there are graphs between entropy and temperature. Okay, those graphs are derived from the basic graphs. Okay, that graphs also we will discuss, and each session, whenever we are discussing each subtopic, we will discuss the previous year questions and some important questions from the standard textbooks. Okay, this class is Clapeyron equation. This comes, it is the application of thermodynamics on phases of the system, different phases. When one phase, suppose your water is converted into gas, so during that change, what the thermodynamics tells us, how do we calculate the enthalpy changes, everything that comes under Clapeyron equation. This deals with the application of your thermodynamics for the phase changes. So, and then the very important topic, entropy. Here itself, you will be introduced with the Gibbs-Helmholtz free energy and the work function, etc. And this is also a very important topic. I will teach you with the tricks as well as the concept wise also based upon the time. Here I will be mostly focusing on the tricks only. I will not go much into the deeper and why it is derived, all those situations, because that one, whenever if you are interested, you can contact me later on after the examination or whenever you come to the campus. So we can discuss much deeply into the concepts of this one. Okay, then this one is your completely MSc topic, PG topic, the Gibbs-Duhem equation. There, I know that 2-3 times the Gibbs-Duhem equation, that equation relation is directly given in the examination. So that's what, and these are very important, these partial molar properties. So if you read them in a sequence, it never makes you any difficulty in answering the questions. Okay, but what you need to do is that you need to read them in a sequence. And one more suggestion I'd like to give you is that before going for the question, practicing questions for CSIR net, you know that all of you must be knowing that IIT JAM is one MSc entrance examination for different IITs. Okay, IIT JAM, that is supposed to be a BSc level examination. So if you solve those questions, first solve thermodynamic questions of IIT JAM, so that you will have a very good understanding of the basic concepts until at least 3-4 concepts, mostly up to first 3, and some Carnot cycle examples also, and some entropy concepts also. What it will give you is that you will be clarified with your fundamental knowledge up to the BSc level. Then you go for CSIR net, so that makes you easier for understanding and solving the questions. Okay, at present actually I have all the question papers, but I don't have the prepared list of thermodynamics. If I get, I will give you. Otherwise, I will give you the whole question papers of IIT JAM. Pick the thermodynamics questions in that and solve it. Okay. If you solve as many questions as possible, it makes easier for you to reach the barrier of that examination. Okay, so whenever you write the examination in the examination hall, you should get a feel that you are solving your questions at home. Such a level of practice, if you have, it will make you more and more comfortable. When you are confident itself, that your confidence will give you answers for at least 6-7 questions. When you are confused and underconfident, even you are, see, if you are 60%, 70% sure about that answer, you cannot pick because you are underconfident. Okay, so if you do more and more practice at home and go for the examination, you will be confident enough. We will be discussing all these things. Whenever you have any doubt in between, you can contact me directly, or you can ask me when we are discussing these classes. Okay. So, okay, I will start with this, the thermodynamics, the basics. So when we know that, when we start look at the thermodynamics, the first thing that we try to understand is that a system and surroundings. For our convenience and for our understanding, we have divided universe into two things, system and surrounding. System is the one where our studies are concentrated upon. For example, if you are doing a reaction, suppose you are doing a reaction in a round bottom flask RBF, or in a small beaker. If you are doing a reaction in a small beaker, that small beaker is your system, rest everything is the surroundings. Anything around is surroundings. Okay, you are only concerned with the things that are happening inside the system, whether it may be a reaction that is happening, a acid-base reaction, or you are preparing a solution, anything. So wherever your studies are concentrated, that is system, rest everything is surroundings. When you have system, this system is divided for our convenience into three different categories. One is the open system, so where you can transfer mass as well as energy. Suppose if you heat this one, the heat energy will be transferred into the system, and with the heat energy, consider that you are boiling water in a glass beaker. If you are boiling in water, you are giving energy, heat energy to the system. When the heat energy it reaches 100 degrees centigrade, water starts evaporating from the system. So there you are transferring mass as well as energy. So these kind of systems are called as open system. Whereas when you come to the closed system, you cannot, you have closed with a lid. Okay, so you cannot transfer the mass. There is no mass transfer in that, but the energy can be transferred because of the barrier is thermal transferable barrier. So you are, and it is able to take or give back the energy, but the mass cannot be transferred. Such systems are called closed systems. And when you cannot take any mass transfer because you have closed it, so there is no mass transfer, and this one is sealed with the adiabatic barriers, so energy also cannot be transferred to the system. Neither it cannot take or it cannot give. So this is called as isolated systems. Whenever we are dealing with whenever we are discussing the thermodynamics, we will be discussing any one of these systems. Okay, either open system, closed system, or isolated system. In most of the cases, we will be discussing about the closed system. Whenever we go for the open system, I will let you know that what kind of system that we are going for. So open system comes into the picture when you have n changes, that means partial molar properties. In the end, it will come. Okay, so this is about the system, and after this, one very important topic and often confusing topic is the extensive and intensive properties. You must have already read about these. Extensive properties depends upon the amount of the substance. Okay, it depends upon the amount of the substance. Majorly, the examples are the important things that you need to remember, because these are the parameters like enthalpy, entropy, free energy, internal energy. The four thermodynamic parameters, these are extensive properties. Okay, and then volume and mass. If you change the mass, if you take suppose 1 gram of a substance, if you have taken different amount of substance, this property will be changing. Whereas if you go for the intensive properties, this does not depend upon the amount of substance. Okay, suppose concentration. We'll take concentration. For example, suppose you have prepared 1 liter solution, 1 liter 1 molar solution. Okay, you have prepared 1 liter 1 molar solution. 1 molar is the concentration. 1 molar solution, whether you take 10 ml of 1 molar solution or 100 ml of 1 molar solution, the volume is different, but the concentration is the same. When you prepare it, when you have taken a 1 molar solution, whether you take it a small amount or higher amount, the concentration will be same. That means that it is not depending upon how much amount of substance you have taken. Okay, that is called as intensive property. It's a big list, but it's a very important list. One important thing that for you to remember is all molar properties. Whenever you see enthalpy is an extensive property, whereas if you consider the molar enthalpy, it's an intensive property, because the molar enthalpy is for fixed amount of substance. You are already fixing the amount of substance, so it does not further depend upon the amount of substance. Okay. See, simple enthalpy is an extensive property, whereas if you consider the molar enthalpy, then it will be an intensive property. So these are the things. In CSIR-NET, the questions from this may be rare, but it's better for your understanding. You remember these. You can analyze these, why these are intensive property or extensive property. Then, if you are dealing with the two properties, X and Y, they are, how they are related. If you take two extensive properties and combine them, you will ultimately the parameter that you are getting will be again extensive. We will see example in the next slide. And if you divide that one, you will get intensive property, and partial derivative of that one is also intensive. If you take two extensive properties, so the division of them will be intensive, whereas and partial derivative of them is also an intensive property. The example is given here. Similarly, the examples are there for each and every case. If you have both intensive properties, the ultimate results are this one. It will lead to the extensive. One good observation that you can make is, other than x plus y, other than the addition, okay, so two extensive will give you intensive, multiplication or division, it will give you extensive. Two intensive properties, if you take, they give you the resultant parameter will be the extensive one. If you have, suppose one intensive property and one extensive property, so this we cannot do the addition, whereas the x by y, the division will give you extensive and partial derivative also give you extensive. So the example that we can see is the enthalpy. Enthalpy, you can write it as E plus PV, where E is the internal energy. So these two are intensive properties. When you combine them, you will get an extensive. Extensive plus extensive again gives you the extensive property. And we have seen in the first slide itself enthalpy as an extensive property. So nowadays the questions from this basic level are rare, but I'm just giving you a reminder of these properties. They do exist, intensive and extensive properties. And again, that very important process when you are understanding, when you want to understand this thermodynamics, is the different kind of process that we are dealing with. So we deal with the isothermal process. We know that isothermal process is the one that takes at constant temperature. When you have isothermal process, the change in temperature of the system will be zero. System does not have any change in temperature. It happens at a particular temperature. So that is called as isothermal. Thermal represents the temperature. Whereas if you go for isobaric process, so barometer, you know that it is used for pressure. It happens at constant pressure, so the change in pressure of the system will be zero. Similarly, the process that is happening at constant volume is known as isochoric process. And the process that happens at Q constant is called as adiabatic process. Q is the heat energy, the energy that we are giving to the system. So in adiabatic process, what it says is that change in Q is zero. That means that system neither takes the energy or not gives the energy. It's a kind of isolated system. So these are called as adiabatic process, and this is a very important process, cyclic process. Cyclic process is the one, suppose you have two stages in your system, A and B are the two stages. So at one stage you are going from A to B. In the second step you will come back from B to A. So you have completed a circle. So this kind of process is known as cyclic process. So this here is given as internal energy. So internal energy is constant for the cyclic process. So change in internal energy is zero. This is a very important point. So the questions can be asked in part B based upon this. Not only internal energy, any state function. We'll discuss about the state and the path functions. Any state function in a cyclic process is always constant. Okay, so the change in state function in a cyclic process will be zero. So please remember this point. We'll discuss again this point in this class itself. So the change in state function in a cyclic process will be zero. These are the different kind of processes that we come across in reading when you are reading thermodynamics. And then the Euler's theorem. The questions from this one also will be rare, but so this relation will be useful for you in deriving the parameters. Okay, so what the Euler's theorem says is that suppose you have a function z, okay, which is a function of two parameters x and y, and then you calculate the change of that function with respect to parameter x first. Okay, suppose z is there is a change in z with respect to the x, and then there is a change with respect to y. So finally you arrived at a point. Okay, you have calculated by x and y are two parameters. Suppose x is pressure when y is volume. If x and y are changed simultaneously, not at a time, simultaneously, you change the parameter or increase the pressure, calculate what is z at final stage, and then increase the volume and calculate z at that stage. So final z will be same as initially you change the y, calculate the change in z with respect to y, and then followed by with respect to x. So those two will be same if z is a state function. Okay, if you want to know whether the given function is a state function or not, you can apply Euler's theorem. So Euler's theorem says that take two parameters, calculate the change in the function with respect to one parameter 1 first, go for the parameter 2. So the overall value that you will get is 1. If you apply the same thing in other way, apply the parameter 2 first and then parameter 1, the ultimate result that you are getting will, if the ultimate result you are getting will be same, then the function is a state function. So you will get much more knowledge about the state function in the coming slides, because this is happening because, so whatever the way we are going, either go from x and y or y and x, finally you are reaching a destination. State function is the one that depends upon its value, or it depends upon the only state of the function, only state, initial and final state, and it does not depend upon the path that it is following. For example, whether you are going from xy direction or yx direction, finally you are reaching the same destination. So the value you are getting is the same when it is a state function. If in any way, if it is a path function, the value will differ. So Euler's theorem will help you to identify whether a function is state function or a path function. So next will be the cyclic rule. This is very important one for CSIR net point of view, because I can see the questions based upon it. We will be doing the one famous and important question based on this. The cyclic rule says that the cyclic rule basically is, it relates three variables. If you have any three independent variables, cyclic rule gives you a relation between these three variables. For example, you have x and y, x, y, and z as three variables, and you can write z as a function of x and y. Okay. If you can write that, according to cyclic rule, the partial derivative of z with respect to x at constant y. So how to understand this one is z, x, and y. Okay, you write z, x, y. Okay, start from z. Okay, dou z by dou x at constant y. This is the one. This is step one. Next one is, start from this, dou x by dou y at constant z. Okay, you are starting from this, dou x by dou y at constant z. And now you start from this, dou y by dou z at constant x. Kind of suppose you take z as 1, this one as 1, 2, 3. You just keep changing the alternatives. Z by x at constant y, then x by y at constant z, then y by z at constant x. This will be equal to -1. Often the question will be given in such a way that sometimes they ask you direct question. Okay, suppose you take you are given like pressure, volume, and temperature. Okay, this rule is like cyclic rule. You start in any direction. Suppose x, y, or z. You start dou x by dou y at constant z. You make in three different combinations, y, z, and x. If you try to write this kind of relation in any combination, it will be same. Okay. Often the question is, once a question is asked in such a way that the pressure, volume, and temperature are given to you, what it is done is that one of this relation is reciprocal. Suppose here, instead of giving this one, it is given like dou y by dou x at constant z. Okay. So in that case, this cyclic rule is not applicable because this is not obeying the order. Okay, so you will be giving the, in one of the option will be -1, you should not get tempted for that. For that, they will be given another hint or another particular application for another thing like ideal gas. So we'll discuss that one later. But according to cyclic rule, if you follow this particular order, the overall answer you will get is -1. Okay, this is example that is given based upon pressure, volume, and temperature. So if you see dou P by dou V at constant temperature into dou V by dou T at constant pressure into dou T by dou P at constant volume. This is absolutely following that particular order, so the value that you will get is -1. You will be very lucky if you get directly this question, but usually it will be twisted. The example is this one. See, for example, we will take this order itself. Okay, pressure, volume, temperature. Based upon the first one, we take this order. Okay, so it is given as dou P by dou V at constant temperature. So the next should be dou V by dou T at constant pressure. That is fine. Okay, dou V by dou T at constant pressure. Is this following? Dou V by dou T at constant pressure. Fine. Next should be dou T by dou P at constant volume. So this is following. If this is following a similar way, then it will be fine. So now, so when you are asked about the ideal gas, we can apply, you know that ideal gas equation is PV is equal to nRT. When you want to apply, there are two gases. One more thing I would like to mention you is that when you are reading thermodynamics, unless the specifically the system is stated, you have to assume that you are dealing with gas. Either it is a ideal gas or a real gas. Okay, unless it is stated that you are dealing with a liquid system or a solid system, mostly you have to. It should be underlined that you are always dealing with the gaseous state, okay, gaseous systems. So when you are being asked to apply this rule, cyclic rule for ideal gas, what you need to do is that take the ideal gas equation and apply these things. Okay, constant temperature, R is constant, N will be constant, then dou P by dou V will be 0. So we'll solve this question in later section. Yes, I have given you for your reference. Note this down, and we'll look for the answer in the later cases. Okay. So the next important term that we will be often speaking in thermodynamics is state function. Most of your important thermodynamic parameters are state function. Usually the state function is the one. It depends upon the initial and final state only. Whether you go from the initial state to the final state in 2 steps, 3 steps, or 4 steps, or directly in 1 step. If it is a state function, its ultimate value will only depend upon the initial and final state. So the other way is it is path independent. Whatever the way you go, final value that you will be reaching will be same if it is a state function. And another important thing is that it must be exact differential. So the exact differential means there are two kind of differentials that we often write in thermodynamics. So capital D, this dV or du, its meaning is U final minus U initial. Suppose U is internal energy that you are speaking about. The change in internal energy will be the difference in the values of its final state and initial state. In that case, you can write a definite integral called as exact differential. Okay. So if it is not a state function, you need to write a partial differential only. Dou usually represents a partial difference. F is a function I am taking. Dou F you have to write. Whenever you have a state function, you can happily write exact differential, because when you have 2 states, initial and final state, the value will be final minus initial. So du determines the difference in the final and initial state. So these are the functions that are given with the exact differential. Okay. Another one is, so as we discussed earlier, if Z is a state function, then it should follow the Euler's theorem, and their cyclic integral is 0. We will discuss about this one in the next slide, and I will say that in terms of state function, for this exam point of view, this point is really very important. Often you are being asked this question. We can discuss in the end of the class about the questions that are asked based upon the cyclic integral. The cyclic integral, we just know before coming to this, in the processes that we have discussed, for a cyclic process, state function, for any state function, cyclic integral is 0. Cyclic integral is nothing but the state 1 to state 2, if you are going, the overall 1 to 2 and 2 to 1, combinedly the change is the cyclic integral. Okay. So this is much more details about the state function and the parameter. This point, cyclic integral is 0. So suppose this is Z is a state function. These are all the different examples of state functions that you need to remember. And you know, these are like, this is internal energy, this is enthalpy, this is Gibbs energy, and this is Helmholtz free energy. Okay, one thing that you can remember is, anyway, it is a standard procedure that state functions are written with the capital letters. They will never be represented by a small letter. Okay, whenever you are given with this kind of question and a capital letter you are giving, so you can have a blind understanding that the capital letter, usually state functions are represented by a capital letter, so its cyclic integral will be 0. Okay, so this is another example. This will give you a better clarity about what a state function is. Okay, whether you are going straight away from A to B, or you go to some other way and come back to B. So the delta U will be same, because U is a state function. Whether you make 100 turns and come back here, or you go directly, the difference between these two will be same. So I guess this picture will give you much more clarity about what is a state function. And then if there is a state function, there is other kind of functions as well, which are known as path dependent. If you change the path, these parameters will change. Okay, so they are heat energy and work done. Sometimes if you are going directly to the destination, you need to do less work. If you want to go for 1 or 2 more stages, you may need to do additional amount of work. So these are path dependent works. And for path integrals, cyclic path functions, the cyclic integral never be 0. It is non-zero. That means that whenever you change the path, you will have a change in work or energy that is experiencing. Okay, so this is really very important point. You can remember blindly that the path state functions are often represented in capital letters. Path functions are represented in small letters, and for state functions, the cyclic integrals are 0. So now we'll come to one very important, that initial state function, internal energy. So internal energy is the total energy that the system will have. So from there, how to understand this? Suppose you have a gaseous molecules in a beaker or a balloon. These molecules, they never stay intact. Okay, they will have a vibrational motion, rotational motion. They keep moving. So each motion will generate certain amount of energy in molecule. So that combinedly gives the system an internal energy. So without giving any system you take, depending upon its nature, either high or low, definitely it will have some amount of internal energy. So every system will have internal energy, and we know that these state functions that we have studied, the major state function, they are extensive properties. And it depends upon the nature of the system, whether if it is a gaseous state, you know that gases often move a lot, so they will have higher energy compared to the liquids or solids. It depends upon the nature of the system, that how much internal energy a system is possessing, but every system will have its own internal energy. So next point is that work done. We'll come to this work done again, but usually what you should remember is that work done on the system, when you do work on the system, the internal energy of the system increases. Whereas if the system is doing work, internal energy decreases. This is how internal energy changes. I'll have a better explanation here. To understand this one, you can consider yourself as a system. We are always speaking in terms of system. Suppose, consider that you are the system. Okay, whatever you gain is positive to you, whatever you loss is negative to you. Okay, suppose some heat is given to you, or some heat is given to the system. That means that system is gaining heat energy. So you represent this one as plus Q. Suppose system is giving back energy, then system is losing energy, so you often represent this as minus sign, okay? Because system is losing some amount of energy. Suppose the system has to do work, no energy is provided to it. It has to use its internal energy to do the work. So to do the work, some amount of energy is required. So it will have a negative value because system is utilizing its own energy, and in the final state it will have less amount of energy because some of the energy is utilized. Okay, to understand this one and to remember this one, very important and very easy thing is that make system your own. Okay, so if you make system your own, whatever that is given to the system is positive, whatever that is taken up from the system is negative. Okay, so this sign convention is very important when we are doing the work done when we are calculating the work done by a particular system. So according to previous statement, that if the system is doing internal energy, sorry, if the system is doing some work and no energy is provided, then system has to use its internal energy. So the internal energy of the system decreases. Okay, delta U will be negative because it decreases. Whereas if the other case, if you take, if you are working on the system, so you are doing the reverse thing, so you are providing energy to the system, that will be positive. Okay. So with this, these are most of the things, that underlying things when you are understanding the laws of thermodynamics. We'll start a discussion for the first law of thermodynamics. If you take, so this is already known to you from long time, but in broad, first law of thermodynamics is law of conservation of energy. We know that from the definition of law of conservation of energy is energy can neither be created nor be destroyed. Okay, you can only transfer energy from one form to the other form. You give heat energy, extract some work from that, or you ask the system to do work to emit some amount of energy, but it cannot be created. That means that suppose you have 5 joules is the total energy that you have. These 5 joules only can be distributed in one form or other form. It can never be 6. Okay, that is major. In broad, the first law of thermodynamics is that it's so if you want to calculate the change in internal energy, it will be sum of the heat energy and the work done. Okay, this is the mathematical form of the change in internal energy. Suppose you have a system, you are giving some amount of heat energy to the system and you are extracting some work. Okay, so the change in internal energy will be sum of these two. Suppose you are giving 5 joules of energy to the system, okay, and you are extracting 4 joules of work, then remaining will be 1 joule. That means that the system internal energy will increase. Okay, suppose in some cases you are not at all giving any energy to the system, 0 joules is the Q, but you are extracting work from the system, then this will be, suppose 1 joule of energy is extracted from the system. I am writing here minus because you are extracting energy from the system. That means that system is losing energy, so I am taking minus sign. So overall it will be minus 1 joule. That means that without providing energy, you are extracting work from the system, so your delta U will be negative. Okay, so this is broadly the first law of thermodynamics. The mathematical form is the change in internal energy will be the sum of the heat provided and work done. Okay, in broad, it is a law of conservation of energy, that energy can only be transformed from, suppose you cannot generate any new form of energy, only whatever it is available, you can use it. That's it. So now, what we will be going to do in the next slides is that we will discuss more about the work done and heat energy. Okay, so we will discuss in different cases how the work is done, how to extract amount of work, how to calculate the work done in different cases, and how the Q can be calculated in different cases of situations. Okay, like maybe an isothermal situation or adiabatic situation or constant volume condition, constant pressure conditions, how this Q can be estimated, and similarly work can how to estimate the amount of work done by a system. So we'll be discussing more details about these two parameters in the coming slides. If you see work, I'm going a little faster because these things mostly already you know. Okay, so work is majorly, you can write it as opposing force into distance moved. Okay, so you have some amount of force. So this is the basic physics definition for the work. So the opposing force into distance moved. So against a force, if you want to push a piston, suppose this is a piston you have, and you need to move to a distance d. Okay, so the amount of pressure that is acting on P on a piston will be, the force will be pressure exerted on a particular area. Based upon the area of this one, how much amount of force, pressure that you are giving, that is called as force. And depending on the amount of distance that it is traveled, the work will be calculated by P external into A, this is force, into distance. Okay, we can write area into distance as volume. So ultimately what you will get is W is P external into A into D is volume, the change in volume. Here, in this example, what you are doing is that your volume is increasing. This is, when the volume is increasing, this is expansion work. Okay. So when the expansion is taking place, the system is doing work. Okay. System, I have not shown you any Q value. When I did not show any Q, that means that I'm not giving any energy to the system. Without giving any energy to the system, system is doing work. So when system is doing work, it is utilizing its internal energy. So it is losing energy. That's why we use it as a negative sign. Okay. So work will be, this is only sign convention. Overall work will be the external pressure into the change in volume of the system. Okay, so this is the one very important formula that we often use or use to calculate the work or to derive the other equations for different situations. Okay, remember this one. Work will be, it's a very basic phenomena, that work will be the opposing force into distance moved. Means if you want to move some piston against an opposing force, you need to apply some amount of energy to that. That is in terms of work that you are doing. So these are really important for you when you are doing the problems or even you are doing the exercises in thermodynamics, or often in gaseous state also. So please note down this one and remember these parameters. The joule is the form of energy that is often represented either Q energy, or work done is often represented in joules. So these interconversions should be known to you very well. And here also, often you will be asked to convert liter atmosphere into this one in joules. So you should be able to do the interconversion. One good thing about is that these things, if you can remember these things, that is good enough. Otherwise, you will be provided in the exam paper, that CSIR net paper, in the front page, you will be given all these units. I guess so. If not, please have a look at that. Otherwise, in practice itself, if you do many practice questions, you will automatically notified with these values. But these are, I would say that when you are dealing with physical chemistry and when you are dealing with the problems, when you are solving the problems, these These interconversions are really important. If you take any other value, you will end up with a different answer. Okay, so with that, let's have an exercise. Please take this question. Here what is given is that a gas expands. This is an expansion from 5 liter against a pressure of 1.2 atmosphere. That means that you are working against a constant external pressure and no heat is exchanged with the surroundings during the expansion. That means that you are not at all neither you are providing the heat energy to the system or taking that one. So you need to calculate how much work is done in the expansion and what is the change in internal energy of the system. Okay, usually, so when I prepared, I hide these answers, but these are appearing. Okay, I will explain it straight away then. You know that just now we have seen when you are working against a constant external pressure, the relation that can be used for extracting the work done is minus P external into delta V. So minus P external, whenever you are given, remember that you are working against a constant external pressure. Okay, I am stressing because this is very important. Constant external pressure and variable pressure. These are the two things that determines two different processes. If you calculate this one, this will be this liter atmospheres. And now you have this example. Convert this one into joules. For 1 liter atmosphere, the number of joules is this one. This will show you a clear example how to convert the units. Okay. In the previous slide, we have seen that 1 liter atmosphere is equal to 101.325 joules. So 101.325 joules per liter atmosphere. Okay. You will have this one. Finally, you will end up with getting the answer in joules. And now the second question what is asked is what is the change in internal energy? So you know from first law of thermodynamics, change in internal energy is equal to Q plus W. Okay, so here it is given that how much work is, no heat is exchanged with the surroundings. That means neither it is given to the system nor taken back from the system. So Q is equal to 0. When you have Q is equal to 0, delta U will be equal to W. That means work done. So delta U is work done, which is minus 60.8. You can see the minus sign. That means that internal energy is decreased. You can understand from this that there is an expansion work that is done and no energy is provided. So system has to utilize its own energy to do the expansion work. That means that overall in the final stage, internal energy of the system is dropping. That is represented clearly with the negative sign. Okay, now so far we have seen constant external pressure. Okay, so far whatever example that we have seen is against a constant external pressure. If you have a changing external pressure, that means that when you are going from A to B, the pressure is not constant. If your pressure is keep changing at each stage. So these two are really very important to understand. You should be able to distinguish between these two. When you have a constant external pressure, that is called as irreversible process. When you have a variable external pressure, it is often represented to understand a reversible process. Between a reversible process and an irreversible process, a very small difference is there. That suppose you consider this one as equilibrium. Okay, this will be intact. This is called as mechanical equilibrium when the external pressure, the amount of external pressure P(ext) is the same as P, the pressure of the gas, internal pressure. If these two are same, then with equal force, the gas is lifting the lifting this one, and from external force same amount of pressure is applied, so it will not move at all. Okay, so if you change any infinitesimal change, if you give any infinitesimal change, suppose from external, if you add some infinitesimal change dp, it will push downwards. Okay, if you take out the external pressure to an infinitesimal amount, it will move upwards. Okay, the infinitesimal, when I am telling that it is uncalculatable, it means it is unmeasurable. If unmeasurable amount of change is happening with some unmeasurable amount of change, if you are able to make changes in the system, then the system is in reversible process. Remember this one, this is very important, because the consequences of reversible and irreversible process are very different. Suppose with any infinitesimal change you are unable to change the system, then it is irreversible system. That means that the case will be either P external is very much higher than P. So we don't write often P internal, but we write only P. Okay, either is the case. Either that one is higher or this one is higher, so it is not in mechanical equilibrium. With small internal, suppose if this is the case, add a small amount to this one, and the direction of the work will not change because it is very much higher. Either add or remove it, it will again be higher only. So in such case, those cases are usually the irreversible cases. Whereas with an infinitesimal change, if you are able to make the mechanical equilibrium shift in either direction, that is reversible case. This is important because work done, okay, we will discuss this one with example later. Work done in reversible process is always greater than work done in irreversible process. Okay, this will be given to you as a question as well. Work done in reversible process is always, you don't need to think anything. If you have any reversible process, if you are when you are comparing with irreversible process, work done in reversible process is always higher than work done in irreversible process. Remember that one. That is the reason why this is given so much of importance. Okay, now only few slides are left. I will finish it off. Okay, work done for a small change in volume. How to calculate this work done? Okay, we know that V minus P external into dV is the change in for a small change in volume, a small amount of work done is this one. Okay, so we are writing P external to replacing with P because this indicates that you are considering external pressure and internal pressure are same. That means the system is in mechanical equilibrium. If you take the ideal gas case, PV is equal to nRT is the relation, you can replace this one with nRT by V into dV. Okay, so this is for small amount of change in volume. For the whole system, you need to, for the total change in volume, you need to consider total work done. So ultimately, you will end up in getting the relation minus nRT into natural log V final by V initial is the relation when you want to calculate isothermal expansion of an ideal gas. Okay, and it should be reversible case. If it is not reversible case, you happily use the already known expression minus P external into dV. If it is the reversible case, you need to use this one. Okay, I do remember that there is a question based upon directly this relation. Okay. These are some of the examples based upon what we have done only. I will discuss this. You can take this question. These slides will be shared to you, and you can take this question. For irreversible case, we need to use this expression. So the amount of energy that you will be getting is this one. For a reversible case, just now we have discussed that there is a different relation that you need to use. Ultimately, you are getting with an answer of minus 172. If you see, for the same system, all the parameters are same, but the way that you have taken is different. Only you are doing an expansion work against an external pressure, but if you do the work in reversible case, the energy will be, the work done will be lesser if you do in the irreversible case. So the work done in reversible process is always greater than work done in irreversible process. If you observe this one, so all the parameters are the same, but the process is different, which is giving you more amount of work. Okay. These are the examples for you to test your understanding about the subject. Please do this one at home. We will assign, there are questions based upon the topic that we have discussed so far. We will discuss these questions in the next class because of time lag. It is already past 4. Just two questions I will discuss with you to make. So among the work, heat, internal energy and entropy, you are asking about the path function and state function. So this is here given to confuse you, that often it should be given as the small letters. You know that all the state functions, all the important parameters like internal energy and entropy are state functions, and work and heat, always remember these are path functions. Okay, often you will be asked when you are dealing with the path function, 95% you will be asked about work and Q only. So this will be the answer, like W and Q, work function, work done, and Q are path functions, and U and S are state functions. Okay. This is about the cyclic integral that you are given, that we have just discussed, that cyclic integral of a state function is always 0, and other than that nothing is 0. So among these all, if you see, this is a path function and this one is a path function, whereas cyclic integral of you know that internal energy is a state function, so cyclic integral of it must be 0, and this you can roll out. Okay, that's how questions will be asked. We will discuss details of each question in the next class. Okay. If you have any doubts, you can contact me. We will be shared with my details. Okay, thank you for joining this class. I'm ending up this class here, and in the next course, in the next tomorrow class, we will discuss about these questions and further topics as well. Thank you very much.
Okay, thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Excuse me, sir. Hello, sir.